Each ovary contains 250,000 egg cells, which reach full development even before the woman herself was born. The eggs each contain 23 chromosomes, the mother's genetic contribution to her future offspring. During each menstrual cycle, the ovaries produce hormones which stimulate the growth of a single one of these eggs. At the midpoint of her cycle, the follicle, which encloses the egg in its layers, ruptures. This is ovulation. The egg travels through the fallopian tube, which connects the ovary and the uterus, or womb. In the tube, the egg waits for sperm from the father to fertilize it. The fertilized egg, now with genetic material from both parents, moves through the tube to the uterus, where it attaches itself to the nutrient-rich lining. And here, the ovary itself. In cross-section, stained blue for better visibility, we see the hundreds of tiny egg cells. This one is nearly mature and is surrounded by its nutritive layers. When it is fully developed, the follicle which encloses the egg will swell, like with fluid, the liquor folliculi. Inside the follicle, the egg and its nutritive layers floats in this water of life, which has the same salt content as the sea. The swollen follicle here on the left is then gently brushed by the swaying fimbriae, the outermost fringes of the fallopian tube. These fringes are activated by the hormones just before ovulation. They sweep over the surface of the ovary, searching for the newly released egg. As ovulation nears, the fringes become filled with blood. The follicle at the center is about to burst. Directly above the white reflections, the liquor folliculi pours out of the follicle. Concealed somewhere within it is the egg. The fringes search for the newly released egg. It lies here, surrounded by a cloud of its own nutritive cells. It is only the size of a grain of sand. At the far right, the egg is drawn into the fallopian tube. Deep inside the egg is the nucleus of new life itself. This is the mouth of the fallopian tube. Its almost imperceptible muscle contractions move the egg along toward the uterus. Here, the egg has reached the interior of the tube itself. These many folds of tissue are lined with tiny cilia, which maintain a constant, gentle motion that draws the egg along its length. The inside of the tube is actually only about twiceness of a single human hair. It takes the egg 3 to 4 days to travel this distance of only 5 inches. The translucent here lies in a muscle fold deep inside the fallopian tube. On the diagonal edge below the egg, we can see a thin, shimmering layer of the cilia which line the tube. Gently moving the egg along, they are exactly like the cilia of the primitive protozoa. The egg must join with the sperm within 24 hours of leaving the ovary for conception. If no sperm are present, the egg disintegrates, and the same cycle will happen again the following month and throughout all the woman's childbearing years. This remarkable cycle is made possible by complex molecules, the sex hormones. Crystallized and stained, they look like this. Hormones control a woman's entire reproductive cycle. Hormones control a man's reproductive ability as well. Only 7 weeks after conception, the fetal system is permanently sensitized to be male or female by the sex hormones. One fetus will develop ovaries, and its brain will be programmed to release hormones in cycles. It is female. Another fetus will develop testicles, and its brain will release constant low-level amounts of sex hormones. It is male. Seven billion human beings have lived on this planet. 4 billion live here now. And every year, 128 million new ones are born. We have already seen part of the woman's remarkable contribution to this unending process. Now, we will explore the man's. During a man's lifetime, his testicles produce billions of sperm. They are stored here in the epididymis. The Cowper's gland produces a lubricating fluid to aid the sperm's journey. The prostate gland secretes an alkaline fluid to protect the sperm. Together, they produce most of the fluid called semen. During ejaculation, the sperm leave the epididymis, moving through the vas deferens in the body cavity. They approach the seminal vesicles, which release a solution of sugar to nourish them. Cowper's and prostate fluids combine with the sperm, and the blended semen continues out of the man's body through the urethra in the penis. This is the interior of the urethra itself. We are traveling up into the man's body from the outside through the penis. The red areas are blood vessels. The black spots are calcium deposits. In reality, the journey is only 7 or 8 inches long. Ahead, the red area is the opening to the bladder. During sexual arousal, a valve here stops urine from entering the urethra. The valve is now open. Here, near the bladder, the urethra passes through the prostate gland. The walls of the prostate have more than 30 orifices, like these, which squeeze out prostate fluid when sperm pass through the urethra. It is about the size of a golf ball, and it resembles a sponge. Inside, it is filled with the small cavities which produce the fluid. These are the testicles, highly magnified and without their usual protective pouch. Unlike the ovaries, their counterpart in women, the testicles lie outside the body cavity. They are made up of the tightly coiled seminiferous tubules, which have a total 700 feet. In the tubules, sperm are produced at the extraordinary rate of 100 million every 24 hours. In the tissue between the tubules, the sex hormone testosterone is produced. The testicles are the essential male organs of reproduction. They function well only under very specific conditions. One of these conditions is temperature. Sperm are produced most efficiently at several degrees below normal body temperature. These images from a thermal camera reveal the various temperature zones in the scrotum, the pouch of skin in which the testicles are suspended. The white areas are the warmest, and the green ones the coolest. The scrotum keeps the testicles away from the body's heat. This section of one of the tubules in the testicles, stained blue and magnified 2,000 times. At the dense center of the tubule is the transport canal, which carries mature sperm away to the epididymis for storage. The smaller compartments produce many new immature sperm every 36 hours. As the sperm become more mature, they move closer to the central canal. The average man produces over 400 billion sperm in his reproductive lifetime. These sperm, magnified 4,000 times, have been in production for approximately a month. They are tightly packed in the tubule within the testicle, their heads and tails intertwined. Inside the developing sperm head, the normal body cell's 46 chromosomes have been reduced to 23. But this reduction of chromosomes, so essential to future reproduction of the species, puts the sperm in mortal danger. The man's body considers these cells enemies. But the sperm are defended by nurse cells, like this one, and the large cell at the right. They form special protective barriers around the maturing sperm cells. Each nurse cell cares for many sperm at a time. This tendril is part of the remarkable communication network which connects each nurse cell to over 150 separate sperm cells throughout the tubule. The tendrils enable the nurse cells to feed and protect the maturum and to move them closer to the transport canal. This sperm is nearly mature. During its development, it has lain in total passivity in the tubule, being protected and nourished by the nurse cell. When mature, like this one, it is transported by the nurse cell to the epididymis. Millions of sperm are stored in these densely packed tubules, which, if stretched out, would be 15 or 20 feet long. The mature sperm in the epididymis will pass out of the man's body through ejaculation 200 to 300 million at a time. Or they will eventually die and be worked. These sperm carry the man's genetic material, and they are fully mature. But they are not yet able to fertilize a woman's egg. They do not attain that ability until they are actually far up inside the woman's body. They may stay in the epididymis, the bag-like structure on the left, for several. While here, they develop the ability to swim. A sperm propels itself by means of a long tail, a flagellum, which lashes vigorously from side to side. This extraordinary activity has but a single purpose: to deliver the genetic material in the sperm's head quickly and precisely to the woman's egg. On the tip of the sperm's head is a layer of enzymes and enzyme inhibitors. The inhibitors preserve the enzymes, which will be needed later to penetrate the surface of the egg. This is how the sperm's head looks without its enzyme cap. The material of the head itself is loaded with the actual genetic information which will be transmitted to the egg. These are the strands of DNA which will be transformed into chromosomes. This is one of the many fuel packets arranged along the midpiece of the sperm. The fuel consists of sugars, which is converted into energy for the sperm's locomotion. The propulsion system of the sperm's tail is made up of a bundle of cords or filaments. The filaments are covered with tiny hooks. As the hooks intermesh, the whole bundle begins to bend, and the tails of the sperm begin to whip around like this. It is a primitive but highly efficient system of propulsion. The system does not function perfectly every time. On the average, up to 20% of a normal man's sperm are deformed or imperfect in some way. Perhaps one reason why a man produces so very many sperm is that so very many things can go wrong with the sperm themselves. They may have 2 tails, like this one. Some even have 3 tails. In another common deformity, the heads of these sperm appear to be nearly severed from their tails. This sperm has been attacked by bacteria. And this one may have been produced too rapidly. It will never complete its development. White blood corpuscles, the large round cells, are often found together with the sperm. Their presence indicates the likelihood of infection, fever, or even a common cold. Most of these sperm deformities could have been caused by just a slight elevation in the temperature of the testicles. Environmental conditions, too, often damage sperm production. Overcrowding, smoking, chemical pollution of air and water, occupational hazards, radiation, poor nutrition, all part of modern life. Even our modern clothing may affect sperm production. Tight blue jeans, for example, hold the testicles up close to the body, perhaps raising their temperature those few critical degrees. But in spite of such obstacles, human beings have been successfully reproducing for millions of years, seen at enormous magnification. They relay messages of sexual stimulation to the brain, which triggers the complex sequence of events leading up to ejaculation. The length of the penis is made up of many small cavities called erectile tissue. When a man is sexually aroused, this from the brain causes these erectile tissues to become engorged with blood. As we can see in these images from the thermal camera, the sudden flow of blood to the penis raises its temperature. The man's blood pressure, heartbeat, and respiration increase. And the blood causes the penis to become erect and elongated so that sperm can be most easily delivered to the woman's egg. In the epididymis, the hundreds of millions of waiting sperm, which will soon be expelled from the man's body, accumulate in a mass. Arousal peak. The entire male sexual system must function perfectly for ejaculation to take place. Cowper's gland, prostate, seminal vesicles, and epididymis. is the actual journey made by the sperm. At the climax of sexual arousal, the man's nervous system triggers rapid involuntary contractions of the muscles in the walls of the epididymis. These propel the sperm up into the man's body along this tunnel-like tube, the vas deferens. The sperm themselves travel the distance, a little over 12 inches, in only a few seconds. The seminal vesicles release nourishing fructose, which blends with the sperm as they pass by. They mix with the prostate fluid. The blended semen approaches the urethra. Its total volume is actually about 1/2 a teaspoon. This is the last leg of the journey. The semen containing the sperm is forced out through the penis by the man's muscle contractions. And at last, it is ejaculated into the woman's vagina. As the semen enters the woman's body, it immediately slows down and coagulates. Perhaps it becomes thicker to ensure that most of the sperm stay within the vagina. Or perhaps the coagulation is a kind of defense, for the environment in the vagina is extremely acid. The acidity protects the woman against bacterial infections, but it is also dangerously inhospitable to the sperm. Nearly 1/4 of them will die almost immediately. About 20 minutes after ejaculation, the semen becomes fluid again. The surviving sperm become vigorously active, swimming rapidly against the downward current in the woman's body. There is great urgency, for the sperm will remain viable, able to fertilize, for only 28 to 48 hours. This is the sound made by thousands of active sperm. The sperm's great activity has but one goal: to find and fertilize the egg. There are so many of them that success might seem assured. But the barriers, too, are numerous. The high percentage of defective sperm has already lowered the odds. So has the vagina's hostile acid environment. And the woman's own defense system attacks the sperm. They are unwelcome cells from another organism and potential enemies. Her defense cells aggressively protect her from the invaders by destroying them. The sperm are programmed to seek the egg, but some of them try to fertilize the first round object they find, in this case, an ordinary body cell. Still, in spite of the obstacles, hundreds of thousands of sperm make their way up through the vagina to the cervix, the mouth of the uterus, which will lead to the fallopian tubes and the egg. The cervix secretes strands of a special fluid protein called mucin. During ovulation, it is very liquid and easy for the sperm to swim in. The strands of mucin provide tiny channels, less than 1/100th of a millimeter wide, directing the sperm closer to their objective. But many of them never find the strands of mucin, and they will die in the vagina. Those that survive will swim up the mucin channels toward the uterus. They swim in dense bunches. The outer ones may protect the inner ones for acidity and defense systems. Once inside the cervix, the sperm continue on their journey. Some remain here, perhaps to provide a backup for those that continue on. The rest proceed up through the cavity of the uterus in search of the egg. Their number is noticeably reduced. Here, from inside the uterus, we see the openings to the two fallopian tubes. The sperm swim toward them. One leads to the waiting egg. The other to an empty tube. Only half of the few remaining sperm will swim up the tube which holds the egg. The tubes are lined with millions of tiny cilia, the same cilia which helped draw the egg from the ovary toward the uterus at ovulation. These cilia sway constantly, creating a gentle downward current that the sperm must swim against. Some sperm get stuck in among the cells lining the walls of the tube. Others lose their sense of direction. During this part of the sperm's journey, the layer of enzyme inhibitors at the tips of their heads is slowly being worn away. The sperm are fully capacitated and able to fertilize the egg, if they ever encounter it. Of the 200 million sperm that begin this long journey, only about 50 ever reach the egg. The egg is surrounded by 2 layers of the nutritive cells which have nourished it on its journey in the fallopian tube. The sperm immediately releases enzymes break through these protective nutritive layers in order to reach the egg itself. At best, only one will eventually enter and fertilize the egg. The joint force of their exertions starts the egg rolling around like a mysterious celestial body. all the while, the sperm are dissolving their way through the egg's outer layers. The first sperm to reach the egg's membrane is immediately drawn inside. This is the penetrating sperm seen from the surface of the egg at enormous magnification. And this is a picture from inside the egg itself. It has been fertilized now for only a fraction of a second. Here is the penetrating sperm with a circle around it from a wider perspective. Only this single sperm will be allowed inside the egg. A rapid biochemical change took place in the egg's membrane. It is now impermeable to all other sperm. Once inside, the sperm too undergoes a dramatic transformation. It loses its midpiece and tail. The tailless head swells up, almost like rising bread. This hole in the sperm head's covering is the first indication that it is about to rupture and release its precious genetic material. Here, the first strand of genes is making its way out of the sperm into the egg. The genetic material continues to spill out from the sperm head. Its tightly packed molecules contain the father's hereditary message. They almost seem to have burst by an explosive force. This is an extreme close-up of the genetic material itself. The magnification on the television screen is over 500,000 times. The genetic material of the mother's egg and the father's sperm combine. Two cells have joined to make a single new cell. And within 24 hours, that new cell begins to divide. These early cell divisions of the human embryo have never before been filmed. The fertilized egg now has two nuclei, the small indentations at the center of the cell. The first division is beginning. Now there are two identical cells, still within the same nourishing material of the original egg. No growth has occurred, but rather a distinction between cells. Once it has begun to divide, the fertilized egg is called a zygote. Now there are 4 cells. The divisions happen at such an accelerated pace that there's little opportunity for the new cells to grow before they divide again. Now there are 8 cells. Each new generation of cells in the zygote is smaller than the one before it. Another division, and another. As the zygote divides along the tube toward the uterus, now it has become a dense, compact cluster of many cells. And after 5 days, it is called a blastocyst. It is still no bigger than the original egg. Its center is filled with liquid. Within 10 days of fertilization, the blastocyst implants itself firmly in the lining of the uterus. Already, the mother's hormones are directing changes in her body to prepare it to support the growing embryo. Barely visible to the naked eye, the embryo will be nourished by the lining of the uterus and then by the placenta. After 2 weeks, the embryo is elongated. It is barely 1/10 of an inch long. At the top, what will become its head and brain. Below, at the tail, the embryo is firmly attached to the placenta. Nourish it. At 4 weeks, the embryo has arm buds and is distinctly curled. It has the beginning of eyes. At 5 weeks, the nose begins to take shape. At 6 weeks, leg parent. The embryo is less than ½ an inch long. It floats inside the fluid-filled amniotic sac. Its spine is clearly visible. At 7 weeks, the embryo is 3/4 of an inch long. It can move its hands, on which there are clearly defined fingers. Its internal organs are visible. The eye lenses are formed. The skull bones, rich in blood vessels, are growing together at an angle at the crown of the head. At 8 weeks, the fingers of the hands are well defined, and the toe joints of the feet are clearly visible. At about 10 weeks, the embryo is considered a fetus. It can move actively. There is a suggestion of an ear. It is 2 inches long, has the stump of a tail. At 11 weeks, it is 2½ inches long. At 12 weeks, 3 inches long. Here, the umbilical cord, connecting the fetus to its food supply. By 14 weeks, it can bring its hands together and suck its thumb. By 15 weeks, the sensory organs are nearly completely formed. And by 16 weeks, it is actively turning inside the mother. This fetus is 18 weeks old. It is 5½ inches long and shown 15 larger than its actual size. Its mouth and lips are fully formed, and it has the strange nasal plugs whose purpose is not yet understood. The eyes of the fetus are closed, but it can see. This sound is made by the fetus as it breathes in amniotic fluid in what is known as fetal respiration. It brings the fluid in through its mouth and then breathes it out again. The umbilical cord is the fetus's link to its source of life, the mother. Here are the fetus's sex organs. All its important physiological systems have developed. But it will be at least another 8 weeks before the fetus has even a remote chance of surviving outside its mother's womb. Whatever signals the beginning of birth is still a mystery. But when the fetus is ready to be born, the uterus begins its powerful contractions, and the process of birth begins.
Pull your legs right in. Keep it coming in. Pull them right in. Keep it coming. Take another quick breath. Oh, push. Hard. Don't stop. Keep it up. Hard. One more in. Deep breath, quick. Push. It's so cold. See this? Can you see this, baby?
Okay, now stop pushing.
Stop pushing. Beautiful job.
There he is. Gonna suck out his little nose now so we can take some nice, clean first breath. Nothing's little about this baby. The stomach. Another girl. Another girl.
Happy birthday.